All right, so here is how you use the limit comparison test to establish the divergence of this sequence. So here's what we did. We tried to compare it to square root n over n because we know that's a p-series with p less than 1, so it diverges. But the comparison test failed because I needed my terms to be larger than that divergence series, and they're not. They're smaller. So now I'm going to try something called the limit comparison test. So the limit comparison test requires me to examine the limit as n approaches infinity of a sub n over b sub n. Now, a sub n is one of the sequences, and b sub n is the other one, and it doesn't matter which one is which. So I'm going to choose root n over n to be my a sub n. So I'm going to look at the limit as n approaches infinity of square root n over n over, my b sub n, which is my series that I'm comparing to, which is square root 1 plus n over 2 plus n. So generally, you're going to be writing these compound fractions. They're very ungainly, so it is certainly appropriate to right away just rewrite those. Like in most cases, I would not even write this. I'm just writing it to show you where things are coming from. I would right away write this as square root n over n times 2 plus n over square root 1 plus n. All right, that's the limit that I've got to investigate. All right, so then that equals the limit as n approaches infinity. So what I'm going to do is just put together the factors that have matching degrees. Like these are degree 1/2, these are degree 1. So I can think of it as 2 plus n over n times square root n over square root 1 plus n. Now, there are various ways to get the limit from here. In fact, you can break this way down, as some people do, multiply the top and bottom of this fraction by 1 over n, and multiply the top and bottom of this fraction by 1 over the square root n, and you can get that, nice justification. I don't think we need to justify that thoroughly. I would just look at this and say this is the limit as n approaches infinity of 2 plus n over n. And I am going to just split up the limit. Arguably, you would not have to do this step, square root n over square root 1 plus n. So what I've broken it down into is things whose limits are clear. This limit is clearly 1. All right, that's just 1. So this equals 1 because the degrees match and the ratio of coefficients is 1. This limit is a little bit less obvious, but it basically works like if you just think about it. This is like n to the 1/2 power, and this is like n to the 1/2 power. So they're really like matching coefficients, and it's still 1. So we get 1. All right. Now, what is important about the number 1? The fact that it's positive and finite. So I could say like this is an element of 0 to infinity. That's going to be my favorite way to say it. But you could say 1 is a positive finite number, and you would be equally correct. And once we establish that, then what we know is that the sum a sub n and b sub n share either convergence or divergence. So now all I need to complete the justification is to say that sum from n equals 1 to infinity of square root n over n diverges because it is a p-series. Now I'm really telegraphing this, but I think this would fly. This would get you full points on AP exam and would be understood by a mathematical person. The sum from n, except that my infinity looks like a 0. Sum from n equals 1 to infinity of root n over n diverges because it's a p-series with p equals 1/2, which is less than 1. All right, and then I get to state my conclusion, which is sum n equals 1 to infinity of square root 1 plus n over 2 plus n also diverges. Whatever this one does, that one does. They do the same thing because they are linked by this finite positive limit. Diverges. And then the crucial justification I need here is by limit comparison test. That's the justification. All right, so what are the elements of the justification that are required here? We have to have cats casting shadows. We have to have, let's see, we have to calculate the limit, all of this calculating the limit. We have to say what the limit is. We have to say that the limit is a positive finite number, or say that it's in the interval 0 to infinity. We have to say that the comparison series either diverges or converges, and why. and then we state our conclusion and justify by limit comparison test. And that's your standard application of the limit comparison test. I think I will split to another video before doing the next one.